We're talking electron orbitals.
Yeah, getting down to the basics.
And you might think electron orbitals sounds like, something you learned in high school chemistry and haven't thought about since. Like some dusty old physics.
Right.
But this is like the hidden architecture that determines how every single atom behaves.
It really is?
How they link up, how they form molecules, and ultimately how literally everything around us is made.
Yeah.
So the source material we have today is actually this really deep quantum mechanical analysis.
Oh, cool.
And those simple diagrams we always see of those? Like, electrons orbiting the nucleus?
Right, yeah, those classic diagrams.
We want to go way past
Get
that.
into the nitty-gritty.
Yeah. We really want to unpack the quantum mechanical basis of what an electron orbital really is.
Awesome.
Look at their shapes, which are actually super surprising.
Yeah, some of them are really wild.
And talk about the implications for chemistry and material science.
Yeah, I'm excited to get into it.
It's going to be fun. It's going to be like we're, getting a whole new appreciation for the essence of matter itself.
Definitely. It's easy to just, take for granted the periodic table and how predictable elements are when they combine. But, the reason for all of that is how the electrons are behaving in those atoms. And orbitals are, like, the key.
Yeah, and we're so used to thinking of atoms like the basics. But even those are built from even more fundamental pieces, right?
Exactly. Yeah.
So I think we need to do like a little bit of a historical tour first.
Yes, set the stage a little bit.
Set the stage. Like
yeah.
Early on, those early ideas about atoms were pretty classical.
Oh, yeah. Super classical.
Alton was just like, these are indivisible building blocks.
Right, little billiard balls bouncing around.
Yeah, exactly. Then Thomson, he gave us the plum pudding model.
Oh, the pudding.
With like the electrons scattered like little raisins.
Yeah, just like studded in this positive dough.
Exactly. And then Rutherford.
Yeah. Rutherford's experiment was so important.
Yeah. With that gold foil, he revealed the nucleus.
Right.
And we got electrons orbiting it like little planets.
Well, like a little solar system, yeah.
But, I mean, these are all rooted in, like, classical physics.
Oh, yeah, for sure.
Thinking of electrons as these, like, tiny little particles with these really well-defined paths.
Yeah, and that's where it kind of breaks down, right?
Right, yeah. Like, if you think of it like that, how come when you get an excited atom, it only emits very specific colors of light?
Yeah, and that really couldn't be explained. And also, like, the stability of an atom itself, if you've got these electrons whizzing around, they should just radiate energy and collapse into the nucleus. It just didn't make sense.
Totally. And that's where we get to the 1920s and quantum revolution.
Boom. Quantum mechanics.
This is a real paradigm shift. So we have de Broglie. He throws this intellectual grenade, which is wave-particle duality.
Yeah, wave-particle duality, that's like the foundation.
Yeah, particles can act like waves.
It's mind-blowing. And it's not just, some abstract idea. That was the thing about it. It explained why electrons could only have these very specific quantized energy levels.
Yeah, and if you think about it visually, like a guitar string,
right,
it can only vibrate at certain frequencies to make those standing waves.
Yeah, and that's exactly what electrons in the atom are doing. They're like standing waves that exist at these specific energy levels.
Exactly. And then we get Schrödinger in 1926.
Oh, Schrödinger. This is where it all gets, like, really serious.
And he has his famous equation now. But it's not an equation describing the path of a particle.
No, it's describing the behavior of the electron as a wave.
And that's where we get these wave functions represented by psi.
Right, psi, that's the blueprint of the quantum state of the electron. It tells you everything you need to know. Its energy and its probability of being in different spots in space.
Right. And it's not like a literal picture of where the electron is at any given moment.
No. And that's where Max Born comes in. If you square the wave function, the psi squared, you get the probability density. So that gives you the likelihood of finding the electron at a specific tiny volume in space.
Okay, so it's all about probabilities now. It's not like the electron is here. It's like, it might be here.
Yeah, exactly. And it's tied to Heisenberg's uncertainty principle, too.
Oh, the uncertainty principle.
The more precisely you know the position of an electron, the less precisely you can know its momentum. It's like this fundamental limit.
And vice versa, right. So it's not even like a limitation of our instruments. It's like baked into the fabric of reality at this level.
Exactly. Like you can't get around it,
Okay, so I think it's time to really nail down this key concept. We're moving from orbits to orbitals. So we're leaving behind the classical picture.
Right. Like we're not thinking about little marbles whizzing around a nucleus anymore.
No, exactly. Like little planets. We're going into this quantum realm where we're dealing with orbitals. And these orbitals are three-dimensional regions of space where the electron has a high probability of hanging out.
Yeah. And it's a huge shift in how we think about the atom.
So what are the classical ideas about electrons that we're just checking out the window
Yeah.
with this quantum view?
Well, I mean, deterministic paths, that's got to go. We're not dealing with nice, predictable trajectories anymore. And then this idea that you can know both the electron's position and its momentum with perfect accuracy, that's out too.
Right.
And then this idea that electrons could have any continuous value of energy. Nope. Energy in an atom is quantized. You can only have certain discrete levels.
So like a staircase, not a ramp for those energy levels.
Exactly, yeah. And finally, this simple, visualizable picture of the electron as this tiny sphere following these fixed paths, that's gone.
Yeah.
We have to replace that with a more abstract mathematical description based on probability distributions.
Right, so we're getting to the heart of the matter. And the heart of it is the Schrödinger equation.
Yeah, that beautiful equation. H_psi equals E_psi.
So that's H, which is the Hamiltonian operator.
Right. Don't get scared by the name. It's basically a fancy way of describing the total energy of the electron.
So we're talking kinetic and potential energy all bundled into one.
Exactly. And then CSE, that's our wave function.
And E is the energy that's allowed for this electron.
And if you solve that equation for the electrons in an atom, that's what gives you the mathematical descriptions of the orbitals.
Okay. And for simple atoms, like just a nucleus with one electron, like hydrogen, you can solve that equation cleanly.
Yeah, it's relatively straightforward for those.
And the solutions you get, the wave functions, tell us what possible states the electron can be in.
Right. And each state then corresponds to a specific orbital with its own, characteristic energy and spatial distribution.
Okay, so CSI, the wave function, it's not just like one single thing, right? It can be mathematically broken down into two parts.
Yeah, it's got the radial part, R of R, and the angular part, Y of theta and phi.
All right, so let's unpack that. R of R, the radial part. What does that tell us about the orbital?
Well, that's all about the distance from the nucleus. It basically tells you how the probability of finding the electron changes as you move outwards. Like, imagine you're drawing a line straight out from the center of the atom. The radial part gives you the probability profile along that line.
Okay. So it's like the probability is a function of distance.
Exactly, yeah. And then the angular part, that tells you about the direction, like the shape of the orbital in 3 dimensions.
So it's kind of telling us, like, if we think back to those simplified diagrams, it's telling us, like, is it spherical? Or, like, is it that dumbbell shape?
Yeah, exactly. You can think of it as defining those lobes that we see in those visual representations.
Okay. So radial part is giving us, like, a sense of size, and the angular part is giving us shape and orientation.
Yeah, exactly.
So we've got these orbitals. And then to really nail down a specific electron orbital, we have to talk about the 4 quantum numbers.
Ah, the quantum numbers? Yes, the electron's address.
Yeah, the unique ID within the atom. So we've got N, the principal quantum number. We've got L, the angular momentum quantum number. And then we've got M sub L, the magnetic quantum number. And last but not least, N sub S, the spin quantum number. So let's go through these one by one.
Okay, sounds good.
So N, the principal quantum number. What's that one telling us?
Well, N can be any positive integer, 1, 2, 3, and so on. And it's basically telling you the energy level of the electron and the overall size of the orbital.
Okay, so like higher N, higher energy.
Exactly. Higher energy and larger orbital. So the electron is, on average, further away from the nucleus.
Okay, so we think about that classic image of, like, the rings of electrons around the nucleus.
Yeah, it's a little bit like that, though not exactly. Remember, we're not thinking about fixed paths anymore.
Right. Probability clouds, not path.
Exactly. And for hydrogen, that simplest atom, the energy is solely determined by N.
Okay.
And there's actually an equation for it. It's E equals minus 13.6 electron volts divided by N squared.
So that really shows how it's quantized, right? Only certain very specific values are allowed.
Exactly, yeah. It's not this smooth continuum of energies.
So that's N. Now we've got L.
Yeah.
What does that tell us about the electron's orbital?
So L can take values from 0 up to N minus 1, and it dictates the shape of the orbital.
Okay.
And it's also related to the angular momentum of the electron. So we usually use a letter code to represent the value of L. So L equals 0, that's an S orbital.
Yeah.
L equals 1. 1, that's a p orbital. L equals 2, that's a d orbital. And L equals 3, that's an f orbital.
Oh, okay, yeah, so those are the shapes we see, those simplified diagrams.
Exactly. And, it's interesting for hydrogen-like atoms, orbitals with the same n but different L values actually have the same energy.
Okay, that's interesting.
Yeah, they're called degenerate. But once you have more than one electron, things get a little more complicated.
Yeah, because now you have the electrons interacting with each other.
Exactly.
Okay, so M sub L, the magnetic quantum number, what does that one do?
So M sub L can take values from -L to +L, including 0, and it tells us the spatial orientation of the orbital.
Okay.
So for a given L, you have 2L plus 1 possible orientations.
Okay, yeah.
Think about p orbitals. L equals 1, right? So M sub L can be -1, 0, or +1. And these correspond to the p sub x, p sub y, and p sub z orbitals.
Oh, yeah.
The dumbbell shapes oriented along the different axes.
Okay, yeah. And in the absence of a magnetic field, those orbitals would be degenerate, right?
Yeah, exactly. But if you apply a magnetic field, they split into slightly different energy levels, hence the name magnetic quantum number.
Okay, that makes sense. And then finally, the spin quantum number.
Right. M sub s. Now this one, it's a little different because it doesn't come directly from solving the spatial part of the Schrödinger equation.
Oh, okay.
It describes the intrinsic angular momentum of the electron. People often visualize it as like the electron spinning.
Okay, so it's like spinning on its axis.
Yeah, but that's just a classical analogy. It's not like a perfect picture. This intrinsic spin is just a fundamental quantum property.
Okay, yeah. I mean, it's not like we can, zoom in and see it spinning.
Exactly, yeah.
Yeah.
And the spin can only be +1/2 or -1/2.
So we call that spin up or spin down.
Yeah. And it's important because it actually creates a tiny magnetic moment for the electron. And it also helped explain some really fine details in atomic spectra that couldn't be accounted for just with the other 3 quantum numbers.
Okay, so these quantum numbers, they're not just randomly assigned. There are these fundamental rules governing which combinations are allowed, right? And one of the most important is the Pauli exclusion principle.
Right. That's like the traffic cop of the atom.
So what's the basic idea there?
It says that no 2 electrons in an atom can have the same set of all 4 quantum numbers.
Okay.
And since each orbital is defined by a specific combination of n, L, and m sub L, that means each orbital can hold a maximum of 2 electrons. And those 2 have to have opposite spins, different m sub s values. So it's kind of amazing when you think about it. This seemingly simple rule, this is why the electrons don't all just collapse into the lowest energy level.
Right.
It's the basis of the shell structure of the atom and ultimately the periodic table.
Yeah, it's like the bedrock, right?
Yeah.
It just cascades from this one principle.
Exactly, yeah.
Okay, so we've got these orbitals, which are regions of probability.
Mm-hmm.
But how do we actually visualize where that electron is likely to be in these regions?
Right, well, we can talk about the probability density.
Okay, yeah.
That's I². And at any given point around the nucleus, it tells you the probability per unit volume of finding the electron right there.
Okay, so it's like how concentrated the probability is at that point.
Exactly, yeah. And to visualize it, we often draw these surfaces that enclose a certain percentage of the electron probability.
Okay, yeah, like 90% or something.
Yeah, exactly. That gives us a kind of visual sense of the shape. But to really see how the probability changes with distance from the nucleus, we use something called the radial distribution function.
Okay, so that takes into account that as you move further out, the volume of that spherical shell at that radius, it increases with the square of the radius.
Exactly. So it's a bit more mathematically involved, but it gives you a better sense of where the electron is most likely to be found at different distances from the nucleus.
Okay, that makes sense.
Right.
And these distributions, they're not just uniform, right? There are these points where the probability of finding the electron drops to 0. Those are the nodes.
Right, the nodes, yeah. And there are actually 2 types of nodes. You've got radial nodes, which are like spherical surfaces at a specific radius where the probability just vanishes.
Okay.
And then you've got angular nodes, which are like planes or sometimes conical surfaces where, again, the probability of finding the electron is 0.
Okay. And these nodes, they're not just some mathematical quirk. They actually influence how the different orbitals interact with each other when forming bonds.
Yeah, exactly.
Okay. And we also briefly touched on the ideas of penetration and shielding. How do those concepts relate to all of this?
Right. So if you look at orbitals with the same principal quantum number, so the same n, but different angular momentum numbers, so different L, you find that some orbitals have a higher probability of being found closer to the nucleus than others.
Okay.
That's what we call penetration. So an s orbital with L equals 0, it has a higher probability of getting really close to the nucleus compared to a p orbital where L equals 1.
All right.
And this is important because it means the s electron, it experiences a stronger pull from the nucleus.
Okay, so the s electron is getting less shielding from the other electrons.
Exactly, yeah. And that's shielding. It's the idea that the inner electrons are kind of screening the outer electrons from the full positive charge of the nucleus.
Okay, so the penetration of an orbital really affects its energy.
Oh yeah, for sure. Orbitals that penetrate more, they're more tightly bound, they have lower energy.
And that explains why the filling order of orbitals, it's not always just straightforwardly by n.
Exactly. So sometimes you get like 4s filling before third and things like that.
Okay, that makes sense.
Yeah.
So let's talk about some specific shapes now. So we'll start with s orbitals, where L equals 0. You said they're spherically symmetrical.
Yeah, they're perfectly round.
So what else defines an s orbital?
Well, the simplest one, the 1s orbital, that's the ground state of the hydrogen atom, and the probability of finding the electron decreases as you move away from the nucleus, kind of like a fuzzy ball that gets less dense the further out you go.
Okay, yeah.
And the 1s orbital has no nodes. But if you look at higher energy orbitals like 2s, 3s, and so on, they start to have these spherical nodes, regions where the probability drops to 0.
Okay, so it's like a layered structure.
Exactly, yeah.
Yeah.
And the number of spherical nodes is n minus 1. So a 2s orbital has 1 node, a 3s has 2, and so on.
Okay. And s orbitals, they don't have a preferred direction when it comes to bonding,
No, they're non-directional.
which is really important for understanding things like the noble gases, right? Why they're so
Right.
stable.
Yeah, like helium with its filled 1s shell, it's
Yeah.
happy, it doesn't want to bond with anything. And also the alkali metals, they have that single s electron.
So they all want to lose that electron and be like the previous noble gas.
Exactly. And even metallic bonding, it has to do with this spherical, non-directional electron density.
Okay. Let's move on to p orbitals, where L equals 1. Now we're getting some directionality.
Yeah, p orbitals, they're the dumbbell shape. 2 lobes separated by a node that cuts right through the nucleus.
Okay.
And for any n greater than or equal to 2, you've got 3 p orbitals.
Right, so x, y, and z.
Exactly. The p sub x, p sub y, p sub z, they're all perpendicular to each other.
Okay.
And each one has that one angular nodal plane. Now, for 2p orbitals, they have no radial nodes.
Okay.
So it's just that dumbbell shape. But higher NT orbitals, they'll have radial nodes as well, so things get more complicated.
More lobes.
Yeah, you can get more lobes. And it's really important to remember that those 2 lobes of the dumbbell, they have opposite phases.
Okay, yeah.
We usually represent that with different colors.
Okay, and that's super important for bonding because it determines whether the overlap with another orbital is like constructive or destructive.
Exactly, yeah. Whether you get a bonding interaction or an anti-bonding interaction.
Okay, so that's P, and now we move on to D,
D orbitals.
where L equals 2. And these get really complex.
Oh yeah, d orbitals are wild.
What are we looking at here in terms of shapes?
Well, they first show up when n equals 3 or greater. And you've got a set of 5 d orbitals corresponding to the 5 possible values of m sub L.
Okay.
And their shapes are kind of like cloverleaf or like a dumbbell with a donut around the middle.
Okay, yeah.
You've got d sub xi, d sub xe, and d sub yz's. Those all have 4 lobes between the axes. Then there's d sub x squared minus at y squared.
Right.
That one has lobes along the x and y axis. And then you've got d sub z squared, which is like 2 lobes along the z-axis, and then this ring of electron density around the middle.
Okay, so really intricate shapes.
Yeah, and each d orbital has 2 angular nodal planes or surfaces.
Okay.
The third orbitals have no radial nodes, but as always, higher end orbitals start getting more complex.
Okay. And the d orbitals, they're key for the chemistry of transition metals, right?
Oh yeah, absolutely. They influence their ability to form these like really cool coordination compounds
Okay.
with all sorts of different geometries, their oxidation states, their catalytic activity. And when you put a transition metal ion in a non-spherical environment, like surrounded by other molecules, the d orbitals, they split in energy,
Right.
which has a huge impact on their color and their magnetism and how they react.
Okay. So lots going on with the d orbitals.
Mhm.
And then we go beyond d to f.
F orbitals, L equals 3. These are even more challenging.
Mhm.
They show up when n is 4 or greater, 7 of them,
Right?
and their shapes are so intricate. Multiple lobes, 3 angular nodal surfaces, they're just hard to even picture.
Okay, so not easy to draw.
Not at all. The 4f orbitals have no radial nodes, but higher ones will have n-4, and these f orbitals are usually pretty close to the nucleus,
Okay, yeah.
shielded by those inner electrons.
Okay.
And that shielding actually leads to something called the lanthanide contraction,
Oh, the lanthanide contraction.
where the ionic radii of the lanthanides decrease as you go across the series.
Okay, okay. And the f orbitals, they're also responsible for some of those interesting magnetic properties of the lanthanides and actinides.
Yeah, exactly. Lots of unpaired electrons, so lots of possibilities for different spin arrangements.
Okay, okay. And then, I mean, we could go on, right?
Oh yeah, you could have g orbitals, h orbitals.
L equals 4, L equals 5, and so on.
But they're not really relevant for the ground states of the elements that we know. Maybe, for some super heavy element, but those are really getting out there.
Yeah, we're talking like exotic physics.
Exactly. Yeah.
Okay, so we've got this picture of all these different orbitals. But when we have a multi-electron atom, how did they actually fill these orbitals? That's where the Aufbau principle comes in.
Right, the Aufbau principle. It's basically a set of guidelines to help us figure out the ground state electron configuration.
Okay.
So which orbitals are filled in the lowest energy state of the atom?
Okay, so it's like nature is lazy. The electrons want to be in the lowest possible energy levels.
Exactly. And the basic idea is that the electrons will fill the orbitals in order of increasing energy,
Okay.
starting with the lowest and moving up. And there's a general rule for predicting the energy ordering called the n plus L rule. So you add n, the principal quantum number, to L, the angular momentum number.
Good.
And orbitals with lower n plus L values tend to have lower energy.
Okay, that makes sense. So like 1s is lower than 2s, which is lower than 2p, and so on.
Exactly. And if you have orbitals with the same n plus L value, then the one with the lower n value is lower in energy.
Okay, okay. And that's how we get that familiar filling order. 1s, 2s, 2p3s, 3p. But then things get a bit more interesting. Like 4s fills before third.
Yeah, and that's because of all those complex interactions between the electrons themselves, the shielding and penetration effects.
Okay, so it's not always just straightforward.
Not always, no. There are a few exceptions, especially with the transition metals,
Right.
like chromium and copper, where having those half-filled or completely filled d subshells is really stable, so they'll actually do things a little bit differently.
Okay, so the Aufbau principle gives us the general order, but what about when electrons are in orbitals that have the same energy level? Like those 3p orbitals or the 5d orbitals.
Right, so those are degenerate orbitals, and that's where Hund's rule comes in.
Okay, so Hund's rule, what does that say?
It basically tells us that electrons will spread out as much as possible in those degenerate orbitals.
Okay.
So before any one orbital gets 2 electrons, they'll each get 1. And all those single electrons will have parallel spins.
Okay, so like all spin up or all spin down?
Exactly, yeah. And there are quantum mechanical reasons for this. Parallel spins give you something called exchange energy, which makes things more stable.
Okay.
And electrons that are in different orbitals, they're also further apart on average, so they repel each other less.
Okay, so it's all about minimizing that repulsion.
Exactly. And Hund's rule, it's really important for understanding why some atoms are magnetic.
Oh, yeah, right. Because you have those unpaired electrons.
Exactly. And it also helps us figure out the ground state electronic configurations and all sorts of other stuff.
Okay. And then, of course, we can't forget the Pauli exclusion principle. How does that affect things?
Well, that's still the underlying rule, right?
Yeah.
No 2 electrons can have the same set of all 4 quantum numbers. So since each orbital only allows for 2 specific spin states, each orbital can only hold a maximum of 2 electrons.
Okay.
And this is fundamental. If it weren't for this rule, all the electrons would just pile into the lowest energy one's orbital.
Right.
And that's why we have this shell-like structure to the atom.
Yeah.
And why we have the periodic table.
Okay, so it really is like the scaffolding of chemistry.
It really is.
Okay, and speaking of the periodic table, all these rules about electron configurations, they directly lead to the organization that we see in the periodic table.
Oh yeah, the periodic table is basically a visual manifestation of all these quantum mechanical principles.
So the periods, the groups, the blocks, it's all about how the electrons are filling those orbitals.
Exactly. The periods, the rows, they correspond to filling a new principal quantum number shell.
Okay.
So a new value of n. And the length of each period is determined by how many electrons can fit in all those orbitals within that shell.
Okay, that makes sense. And then the groups, those are the columns.
Right. The groups, they represent elements that have similar valence electron configurations.
Okay, so they have the same number of electrons in their outer shell.
Yeah,
And that's why they tend to behave similarly.
exactly. Yeah. Similar chemical properties.
Okay, and then those blocks on the periodic table, the S block, P block, D block, F block, they're literally telling us what type of orbitals is being filled.
Yeah, it's right there in the name. S block, you're filling S orbitals. P block, you're filling P orbitals, and so on.
Okay, okay. And this whole framework, it lets us understand those periodic trends that we see.
Oh, yeah, absolutely. Things like atomic radius, ionization energy, electron affinity, electronegativity, and a whole bunch of other stuff.
Okay, okay. So we've been focusing on individual atoms. But what happens when these atoms decide they want to hang out together to form a molecule?
Right. Well, their atomic orbitals start to overlap,
Okay.
and they mathematically combine to form molecular orbitals.
Okay, so we're like taking the atomic orbitals and merging them.
Yeah, kind of. And one way to think about it is the linear combination of atomic orbitals, or LCAO method.
LCAO.
So you've got two atomic orbitals from different atoms. They can combine in two main ways.
Okay.
One is in phase,
Okay.
where their wave functions kind of add together in the region between the two nuclei.
Okay.
And that gives you a bonding molecular orbital.
Okay, yeah. So the electrons are kind of shared between the two nuclei.
Exactly. And that makes things more stable, lower energy.
Okay.
And then the other way is out of phase, where the wave functions kind of cancel each other out between the nuclei.